Our next speaker is going to be Sam Lichert. Lichert?
Yeah.
Lichert, make sure I got that right. Earth Systems Institute. She's going to talk about modeling how wood is delivered to streams. Help me welcome Sam. Get her up. And you are?
Thanks. Okay, so as Cheryl said, I'm going to talk about wood recruitment modeling in NetMap. And if you've not heard of NetMap, my co-author on this, Lee Bender, will be talking this afternoon about NetMap and the models within it. I'll give you one slide on it. So, it's a set of analysis tools, geospatial analysis tools, and integrated with geospatial data. And it covers, as you see, the different topics I've got up here: aquatic habitat modeling, watershed processes in terms of erosion and sediment, large woody debris supply, thermal loading, different vegetation models, lots of road models, and some other tools that I think of as a sort of miscellaneous but helpful overlap tools, different things to help with analysis. So I think the previous three speakers set this up pretty nicely about the wood in the streams, but I just want to mention briefly, as you know, the legacy of management that's reduced the supplies of large woody debris, and how important it is to create the aquatic habitat, whether it's improving the channel morphology, holding sediment back, providing nutrients for fish, macroinvertebrates, different processes that provide the wood, wildfire and insects, disease, blowdowns, mass wasting, debris flows, as we just heard about, and the mortality from all these different sources, as well as the natural mortality. And now we've got this thing where we focus on what happens in the thinning, and we do this process called tipping, which we're modeling now. And I'll talk more about that as we go on. So we've got a variety of wood models in NetMap, but I'm going to talk about two that are at different scales today. We've got the reach scale wood model and a watershed scale model. And you can see there just a quick cartoon in case there was any confusion. I didn't think there was. So the reach scale is based on a 100-meter reach, or a project scale. We look at selected piece sizes. You can go and alter those. And so it's temporally and spatially explicit, which is what you'd want to do, to look at what happens to your trees, what happens to your management over time, and what's going to happen with your new different buffers, what's going to end up in the stream. And the results of that, I'll show you some of the results of that, different plots for volume of wood and number of pieces. And then the watershed scale, again, temporally and spatially explicit, this time at a cell-based scale. It allows you to do a cumulative effects analysis of different management scenarios, and it's based on the reach scale model. But in this case, it's going to result in different plots and maps. So here's the reach scale. This is the spatial setup. Let's see if I can get this thing to work. So what you can do is put 3 different forest stands in on each side of your stream here. Here's your 100-meter reach. You're going to need the channel width. You're going to need different hill slope gradients for each of these 3 stands. You don't have to put 3 in. There can be 1 or 2 or whatever you want to do, whatever's going on. So the bells and whistles, I've covered the first few there. We can account for bank erosion, for wood decay and accumulation. We've got different taper equations to account for the shape of your different trees. It's not just a cone shape. And we can also account for this thing called tipping. And the idea behind that is it comes from a project that we did where we were trying to figure out, based on reference conditions and thinning, if you wanted to show that thinning was reducing the amount of wood in the streams, if you wanted to then say, well, I need the wood that's going to make up my reference condition, my natural, quote, conditions, I might tip those pieces of wood in the stream. And what happens to that? Instead of just the tree dying and falling in some random direction, you're going to tip it directly into the stream. So you're going to have a probability of 100% that that piece of wood is going to end up in the stream and be hopefully a functional piece of wood. The inputs to this I haven't covered are different forest stand tables, and they can come from the different models that we've heard about today. FES, Organon, Zelig, we've run all those through here. So here's some scenarios that we ran through there. Let's just set you up here for a minute. The left bank, we always use the no action scenario. There was just basically nothing going on. It was, I think it was a dug fir stand. The right bank, we've got these different treatment scenarios. There's about 11 of them. We did a double entry thin to 70 trees per acre in 2010, 2040. All the other parameters we held constant. We didn't want to mess with anything else. We just want to see what was going to happen to the amount of wood based on these different scenarios. There's no action, the thinning, and then we do this thing with the thinning and we tip 5% of the wood, tip 10% of the wood, 15 and 20. And then for our next set of scenarios, we don't have this buffer in here where we're not doing anything. We're going to thin the entire 70 meters. In this case, we had a 10-meter buffer. So we're going to thin that 70 meters and then do the thinning and tipping 5, 10, 15, 20%. So we're trying to see here what happens with and without a buffer, with and without thinning and tipping. Tipping different percentages, obviously. So some results here. The green line is the untreated. Let me back up a little minute here. Two plots. The top one has, I don't know if you can read that, it says no buffer in it, and then that bottom one is the 10-meter buffer. So on this top plot, we're thinning right up to the stream. This line here is basically the left bank on the left and the right bank on the right. So we've got the wood volume in the stream in terms of cubic meters per 100 meters of reach on both uprights, and then we've got years along the bottom here, and we go to about 100 years. So the green line is untreated on both banks, and then when we have a thin that goes in on one bank, this is how the wood volume is reduced. And that was part of our project here, was to figure out what is the wood reduction. So this is going to give you the amount of wood, how it's reduced over the years. And then we came up with this idea of tipping the trees in. This is our first thin here. So you don't see kind of the increase that you see here. So I'll focus more on this. This is the second thin in 2040. And then from here, we're tipping in 5, 10, 15% of the trees. And you can see there's this huge increase in wood, which continues on till, what, almost, 60 years from the start of this simulation. But maybe 30 years after that initial tipping and thinning is put in. And so then you start to reduce your amount of wood. But overall, what I'm going to show you, the cumulative results of that show a little bit of a different picture. This bottom one is basically the untreated and then having the 10-meter buffer in here. And it shows the same results, but it dilutes a little bit because you've got that 10-meter buffer in there until you start on your thinning and tipping. Oops. This is another plot that we put out that's, it's the same scenarios. Again, I've got the no buffer on the top and with a buffer down below. Again, you've got wood volume on the upright, and then you've got distance to the stream. So this is showing you where is that wood coming from. And this is plotted just for the 1 year, it's 2010. So what you're seeing here is the results of the first thin and tip. And basically for the untreated stand, there's actually green in there. It's hard to see, but there is green in there. And then you can see the other lines where the trees were thinned and then they were tipped into the stream. The 15% being the largest amount of wood. Part of the model, when we calculate the tipping, when we do our thin, it's based on the stand. When we do the tipping, we calculate in 1 meter increments away from the stream. So that first meter, whatever the trees are there, if they're within that percentage that's thinned, they're going to be tipped straight into the stream. And this is why you start to see more volume closer to the stream. And it declines as you get further and further away. And that's because the trees, as you're looking at the trees further away from the stream, if they're the same size as the ones close to the stream, those trees are going to be depositing less wood into the stream because of the taper. So this is, I hate it when people put up tables in presentations, but this one was kind of important, I think. So here's your reference condition in the pretty orange there, and you're showing about 271 cubic meters in your reach. And then for these other, I've got all the other different scenarios. I'm down here with the volume on the left, and in brackets is the percent change from that reference condition. So for example, if you had a 10-meter buffer in there and then you did your double thin and you didn't do any tipping at all, you're going to lose 10% of the wood. And this is overall, so this is the area under that curve that I was showing you. This guy? All I've done here is just incremented, just counted up all of the volume under here. And that's why you're starting to see that you know, these values are just 10%. And then you've got a lot more. When you start thinning and tipping your wood in there, you can gain 5% over the time. So this is over the 100 years of simulation, going up to about 20% for a double entry thin, and where you tip 15% of your wood. So we're actually seeing quite a bit more wood in there than our reference conditions. So we look at that, maybe you need to put that amount in, maybe not. So that was the reach scale wood model. Now we're going to go into the watershed scale wood model, which is actually based on the reach scale. We're using the same calculations, the same technology. This is more of a three-step process. It's a lot more computationally intensive. So I'm taking those same stand tables that I used as input. Could be from FBS, Organon, Zelig. And these are pre-processed in the reach scale. Then we're going to go into the GIS and integrate that tabular data with the stream reaches, with the stand polygons, which is what you see here. These are the streams, and the digital elevation model, the DEM, and generate our output. So I've got some different data that I ran through here. This is a watershed, it's about 5 square kilometers in the Oregon Coast Range. The dark purple we can see here are planted stands. And then they've got a buffer in the light purple. The conifer is this dark green. And that's about more than 80%. And we've got some mixed stands here too that are still predominantly conifer, but not quite as much. Some hardwood stands, hardwood buffer areas, all through here. And there's that last color down there, which is about half and half mixed hardwood conifers. So this is the treatment that's we're going to test on here. It's a thin to 70 trees per acre from the bottom, and it's about, this results in about 47% of the watershed being thinned. And this is the this green hatching that you're seeing here. That's this little guy here. None of this one in this particular map. So this is just overlaid on my stand. This is what happens when you have the buffer in here. This is our no-thin buffer, and you can see it from this line here in the little polka dots. It's very girly, isn't it? So this is a result from one of our runs. This is the wood volume. It's a map of the wood volume. Well, and it could also be the number of pieces. This happens to be the volume, but we do put out the number of pieces too. And this is going to show you the sources. Where is that wood coming from? And this is using the no-action buffer, and our year is 2065. So the wood that you're seeing, and I haven't got numbers on here, but it would be in volume per length per year. And the low numbers are the light purple, darker numbers are the higher, darker colors are the higher numbers. And then these blue lines that you see in there are the reaches. And there's areas where I was missing a stand table, or sometimes there's areas where there just isn't any wood, or the pieces are too small to show up in the model. So you're going to see these areas where there just isn't much going on. So let's strip away the background of that, the DEM and the hillshade and all that pretty stuff, and just show you where the thinning was. Remember that's our green hatching here, and the no action is the pink. And then this one below is where it's all thinned. I'm not sure if it's showing up very well. It's not showing up for me very well. But what should be happening here is that basically numbers like this area here, sorry, let me find a good area where this actually thinning, where this is thinned over the, or where you're getting wood volume coming from the no action area, then when you thin it down here, this would actually be a lighter color purple. Same in other areas like this one here, where there's no action, it's darker than the corresponding area down here, where it was actually thinned. So let's take that data and summarize it over all the years. So here we've got our it's actually in this case it's about 200 years wood volume on the upright on both cases. This is the no action buffer, the thinned buffer. We had some issues that one of the stands had data to 2295, and that's why you're seeing this kind of, there's actually some little tiny values in there. So what you're seeing is a high initial mortality. This was in the stand tables. I went in to check on that because I wasn't sure whether that made sense or not, but it's coming in on our stand tables. This was thinned in 2015, and so you see this decrease in wood right around here. And then this area in here is right after the thin for the next, 80 years or so. And you're seeing a lot more wood coming in with the no action buffer versus the thinned area. The line that's showing here is the cumulative percent of the wood volume. And again, this gets higher much quicker in up through like 2050. It's getting to about 80%, whereas 2050 on here, and you're still down here at about 60%. And then you get up to 100% at somewhere in here. And here it just takes that much longer where you've got a little taper.
3 minutes in.
Thank you. This is the same data that you just saw in that other bar graph. What I've done is just break it out by piece size so that you can see, again, with a no action buffer, you've got larger pieces through here, more wood, and it really drops off once you get to about 2100. Whereas here, 2100, you've got a lot more wood coming through after that, and you've got bigger pieces as you might expect from a thinned buffer. This one is just showing the percent changes in wood volume by piece size again. And I wanted to see from the no action to the thin buffer, so it's taking that previous plot and just saying what are our differences here. This is the piece size, this 0 to 10 centimeters, 35, 60, 80, and then the total. So when you have, so when you are looking at your no action, the change when you thin that buffer is you get a decrease in the smaller wood pieces, and you're going to get this increase in the larger pieces. And this is actually 80 centimeters and more. It's going over that. And your total, you end up with about, it's something like 15% less wood. So just in summary, what I've tried to show here, that we've got these multi-scale models, the reach and the watershed scale for management and analysis. It's enabling spatially variable buffers, spatially explicit analysis. So you can check out different designs that you might want to do for different treatments to see what's going to be the impact of wood in the streams, whether it's thinning or buffers or for habitat, and also to try to enhance the aquatic habitat with tree tipping or other types of things. And lastly, some acknowledgements and thanks for people, for Gordy Reeves and Stu Johnson, particularly for our data files, and Jack Sleeper and Dan Miller. Thank you.